Then let's consider the interactions between particles inside big systems. In some solids, all the atoms are connected by covalent bonds. Such solids are called network solids. Typical network solids are diamond, silicon, silicon carbide and silicon dioxide. Atoms in metals are bonded by metallic bonds. We will discuss them in the next chapter. Besides covalent bonds and metallic bonds, all the interactions between particles in a big system are electrostatic. There are 4 basic types of electrostatic interactions depending on the electric properties of the particles. First, the ion-ion interaction. It is also known as Coulomb force. Second, the ion-electric dipole interaction. The electric dipole can be either permanent or induced by an electric field. By default, when we use the term electric dipole, we are talking about the permanent electric dipole, unless other specified. Third, the dipole-dipole interaction. In such interaction, at least one of the dipoles is permanent. There is a special dipole-dipole interaction, the hydrogen bond. Fourth, the interaction between instantaneous dipoles. It is also called the London dispersion force. The forces between charge-neutral particles are van der Waals forces. So, type 3 and type 4 are van der Waals forces. There are other types of electrostatic interactions, such as the quadruple interactions, but we will not discuss them in general chemistry. The electrostatic interaction between 2 particles is described by the electric potential energy between them. It is the electric potential energy of one particle in the electric field of the other particle. The electric potential generated by an ion is shown below. The electric potential energy of the other ion is the product of its charge and the electric potential at its position. So, we can calculate the electric potential energy between 2 ions. It is inversely proportional to their distance. Ionic compounds have cations and anions bonded by electrostatic force. The ion-ion interaction is the strongest in all electrostatic interactions, so ionic compounds usually have high melting points. For example, sodium chloride has a melting point as high as 800 degrees Celsius. However, the strength of ion-ion interaction decreases with the distance between them. When the sizes of ions are large, the interaction becomes weak. That is why some ionic compounds are liquids at room temperature. They are called ionic liquids. As we have discussed in the last chapter, in a polar bond, the electrons are biased to one atom due to the difference in the electronegativities of the atoms. Thus, a polar bond is an electric dipole. A molecule may have electric dipole moment if it has polar bonds. Such molecule is a polar molecule. For example, hydrogen chloride and ethanol are polar molecules. A molecule without electric dipole moment is a nonpolar molecule. For example, hydrogen and nitrogen molecules are nonpolar molecules. Some molecules have zero electric dipole moments even if they have polar bonds. It is because the total electric dipole moment of a molecule is the sum of the electric dipole moments of all the bonds. If the electric dipole moments of the bonds cancel each other, the molecule is nonpolar. For example, carbon dioxide molecule is a typical nonpolar molecule, even though it has carbon-oxygen polar bonds. The electric dipoles of the 2 bonds are same in magnitude but opposite in directions. So, they cancel each other. Similarly, the 4 electric dipoles in carbon tetrafluoride molecule cancel each other. We know that an ion generates electric field around itself. Thus, an electric dipole has an electric potential energy in this electric field. The electric potential energy between an ion and an electric dipole is calculated by the following equation. It depends on their distance and relative orientation. An electric dipole also generates electric field. So, another electric dipole has an electric potential energy in this field. The interaction between electric dipoles is also known as Keesom interaction, which is calculated by the following equation. It also depends on their distance and relative orientation. You do not need to understand the details of the calculations of those energies. The only thing you need to remember is that, on average, there is an attraction between an ion and an electric dipole, as well as between 2 electric dipoles. The attraction between electric dipoles is the main reason why polar molecules condense to liquids. Here, I show some molecules with similar molecular weights but distinct electric dipole moments and boiling points. You can find an increase of boiling point with the electric dipole moments due to the increase of attraction. For example, propane has the smallest electric dipole moment, so the interaction between propane molecules is the weakest, and its boiling point is the lowest. In contrast, the electric dipole moment of acetonitrile is the largest, so the interaction between acetonitrile molecules is the strongest, and its boiling point is the highest. Hydrogen bond is a special type of dipole-dipole interaction. When a hydrogen atom is covalently bonded to an electronegative atom such as nitrogen, oxygen or fluorine, the electron in the bond is heavily biased from the hydrogen atom, leaving a nearly bare proton. This electronegative atom is called a proton donor. The nearly bare proton, which is heavily positively charged, attracts a lone pair from another electronegative atom, which is called a proton acceptor. Such system is a hydrogen bond. Though the hydrogen bond is a type of dipole-dipole interaction, it has many unique characters. First, the hydrogen bonds are shorter and stronger than normal dipole-dipole interaction. For example, hydrogen peroxide and formaldehyde have similar molecular weights, but hydrogen peroxide has hydrogen bonds while formaldehyde has normal dipole-dipole interaction. Thus, liquid hydrogen peroxide is significantly denser. It is the evidence that the hydrogen peroxide molecules are closer to each other. Meanwhile, hydrogen peroxide has significantly higher boiling point. It proves that the interaction between hydrogen peroxide molecules is stronger. Second, the hydrogen bonds are directional and have limited number of bonds for each hydrogen atom. For example, in water, each hydrogen atom is bonded to one oxygen atom via hydrogen bond. The proton donor, proton, and acceptor proton acceptor are in a straight line. The unique characters of hydrogen bond suggest that hydrogen bond has contribution from covalent bonds in addition to the dipole-dipole interaction. The hydrogen bond is extremely important, not only because it appears in water, but also because it also appears in all kinds of biochemical molecules. The double helix structure of DNA and the secondary structure of protein are mainly maintained by hydrogen bonds. For example, the nucleobases G has 2 proton donors and 1 proton acceptor. So, it must pair with nucleobases C, which has 2 proton acceptors and 1 proton donor. We know that a molecule or atom is made of positively charged nuclei and negatively charged electrons. In an external electric field, they experience forces in opposite directions. Therefore, an electric dipole can be induced on a nonpolar particle by an external electric field. The induced electric dipole moment is proportional to the external electric field. The proportionality coefficient is its polarizability. The external electric field can be from either an ion or an electric dipole. Therefore, there is an interaction between a nonpolar particle and an ion or a polar molecule. The electric potential energy between an ion and a nonpolar particle is calculated by the equation below. The electric potential energy between a polar molecule and a nonpolar particle is also known as the Debye interaction. It is calculated by the equation below. You do not need to understand the details of the calculations of those energies. The only thing you need to remember is that, on average, there is an attraction between an ion and nonpolar particle, as well as between a polar molecule and a nonpolar particle. The ion-nonpolar molecule interaction can be understood using such example. When the fur of the cat is charged, it attracts foam which has no permanent electric dipole but induced electric dipole by the electric field of the charged fur. The polar molecule-nonpolar molecule interaction can be understood from the attraction between a permanent magnet and iron. Iron is ferromagnetic and has induced magnetic dipole in the external magnetic field of the permanent magnet. On average, a nonpolar molecule has no electric dipole, so there should be no dipole-dipole interaction between nonpolar molecules. However, according to quantum mechanics, the electrons are not static in the molecule. They can be anywhere, making the molecule an instantaneous electric dipole from time to time. This instantaneous electric dipole makes an induced electric dipole on another nonpolar molecule. Thus, there is an attraction between two nonpolar molecules. This interaction is called London dispersion force. It is the weakest among all the dipole-dipole interaction. The London dispersion force has a great influence on the properties of nonpolar molecules. Generally speaking, larger interaction area leads to a larger dispersion force. For example, pentane and 2,2-dimethylpropane are isomers. Pentane molecules have larger interaction area because they are linear. Thus, the dispersion force between pentane molecules are greater, and it has a higher boiling point. Here, I summarize all the important electrostatic interactions between molecules and ions. They all decrease with distance between the particles, but with different rates. The faster the interaction decreases with distance, the weaker it is. For example, the ion-ion interaction is the strongest while the London dispersion force is the weakest. The interactions between the particles determine the macroscopic properties of matters, such as the boiling points. That is, the ionic compounds have the highest boiling points, polar compounds have medium boiling points, while non-polar compounds have the lowest boiling points. Surface tension is another phenomenon to show the interactions between particles. We know that the energy increases with distance between particles. So, the total energy of a system is minimized when the particles are next to each other. However, any condensed system has a surface. The particles on the surface have higher energy than those inside, because they have less interactions with other particles. The extra energy per unit surface area is the surface energy. It is also called surface tension because there is a tendency to reduce the surface area to lower the energy. For example, liquid mercury tends to form rounded shapes in a petri dish. It is neither the state with the lowest gravitational potential energy nor the state with the lowest energy on the surface, but the state with the lowest total energy. Here, I show you the relationship between the surface tension and the particle-particle interaction of a few typical liquids. You can see that mercury has the highest surface tension because the metallic bonding is the strongest in this list. Pentane has the lowest surface tension because its London dispersion force is the weakest in this list. Water and formaldehyde have medium surface tensions because their dipole-dipole interactions in medium. Water's surface tension is higher than formaldehyde because water also has hydrogen bonds, which is stronger than normal dipole-dipole interaction. A phenomenon related to surface tension is wetting, which we can see with our eyes. Wetting is the ability of a liquid to maintain contact with a solid surface. The degree of wetting is measured by the contact angle. When liquid contacts a solid surface, there are three interfaces. The solid-liquid interface is denoted by SL. The liquid-gas interface is denoted by LG. The solid-gas interface is denoted by SG. The contact angle is defined to be angle between SL and LG interfaces. A contact angle between 0 and 90 degrees is a high wettability. A contact angle between 90 and 180 degrees is a low wettability. A solid with high wettability with water is hydrophilic. A solid with low wettability with water is hydrophobic. The surface energy increases with the surface area. The increase of surface energy is equal to the work done to the surface, which is the force on the edge of the surface multiplied by the distance of edge motion. Thus, surface tension is the force per length of the edge. The contact angle is determined by the force equilibrium at the solid, liquid and gas interface. When the system is stable, the surface tension in the direction parallel to the solid surface must be in equilibrium. So, we can have the following equation about contact angle. We can use this equation to understand the wetting phenomenon. For example, mercury has very high and almost identical surface tensions with both glass and air. Therefore, it has very large contact angle and very low wettability with glass. Solid and liquid with similar polarities have low interfacial energy. Thus, they have low contact angle and high wettability. For example, water and glass, which is based on silicon dioxide, are both polar. So, glass is hydrophilic. However, if glass surface is contaminated by oil, which is non-polar, the glass becomes hydrophobic. Therefore, we can speculate whether the glass is clean or not by observing the shape of water on it. Surfactants are compounds which lower the interfacial energies between a solid and a liquid to improve their wettability. Surfactants in aqueous system have both hydrophilic and hydrophobic groups. Such kinds of molecules are so-called amphiphilic. For example, sodium stearate is a typical surfactant of aqueous system found in many detergents. In it, the carboxyl group is polar and hydrophilic. The aliphatic chain is nonpolar and hydrophobic. When dissolved in water, amphiphilic molecules form a structure called micelle. The hydrophilic heads orient outward to contact the surrounding water, while the hydrophobic tails cluster in the center to avoid the contact with water. Other nonpolar molecules such as oil can be stored in the center of micelle. Thus, they do not contact the water, so their high surface energy is avoided. The mixture of water, surfactant and oil are called emulsion. The surfactant also reduces the surface energy between solid and water. With surfactants and water, oil can be removed from solid surfaces such as cloths and dishes.